Hi everyone, I'm glad to present our work, GAPSLAM, blending Gaussian approximation and particle filters for real-time non-Gaussian SLAM. This is joint work with John Leonard. The problem we consider here is estimating posterior distributions encountered in SLAM. There are two motivations. The first one is that we want to understand the uncertainty in localization and mapping. The second one is that given the understanding of the uncertainty, the robot can plan how to reduce the uncertainty for safe navigation and active perception. We just review two standard approaches for posterior inference. The first one is the Gaussian approximation. As seen in the figure, the Gaussian approximation is only a local approximation of the distribution. The second one is RBPF. RBPF is known for non-Gaussian estimation, but suffers from poor scalability. We blend the complementary strengths of both methods and achieve both good scalability and expressivity. GAPSLAM consists of two key elements, namely the adaptive probabilistic modeling and the uncertainty-aware reinitialization. On the left-hand side, the adaptive modeling means that we compute a Gaussian approximation for all the variables, and at the same time, we only use the particle filters to describe very uncertain landmarks. On the right-hand side, I'm showing you how the Gaussian approximation and particle filters help each other. The first arrow shows that the Gaussian approximation provides robot-pose distributions. Given robot-poses, particle filters can generate landmark samples. And then the second arrow denotes that we can pick the best sample to reinitialize the landmark in the Gaussian approximation. The reinitialization simply means resetting linearization points in the optimization solver for computing the Gaussian approximation. We have two sets of results. The first set is a range-only SLAM experiment where we validate our implementation and show competing methods. In the second set of experiments, we demonstrate that the method can be scaled to 3D. We used the plot dataset for range-only SLAM experiment. The measurements in the dataset were gathered on a mobile robot operating in a planetary environment. We used the real odometry data and the distances to 4 landmarks to estimate the robot path and the landmark locations. I'm showing you samples generated by different methods for representing the posterior distributions. In addition, for GAPSLAM results on the left, I'm also showing you confidence intervals of Gaussians as the green ellipses. The NSFG result in the middle is a pure Monte Carlo method for generating the reference solution to the posterior. The right-hand side is a competing method based on RBPF. You can see that the samples generated by GAPSLAM resemble the reference solution in the middle the best. Samples by RBPF mistakenly capture some spurious modes. The data in the object-based SLAM is just RGB videos. We derive two types of measurements from the data. The first one is visual odometry, which provides the dead reckoning path. The second kind of measurements is object detections. We detect many classes of objects, such as cups and cereal boxes. We simply model 2D centers of object masks as bearing measurement to the 3D centers of objects. So basically, these bearing measurements will constrain the drift in the dead reckoning path. Here is the video. On the left, I'm showing object detections and the projection of the map. On the right, I'm showing the 3D SLAM results. Objects in the map are represented by samples or ellipsoids, depending on the level of uncertainty. In the beginning, when we only have few bearing measurements to an object, the samples in 3D are distributed in cone-shaped space. As we move on and observe the same object multiple times, the samples gradually converge to a small area, visualizing how the posterior of that object evolves. And then we will remove the particles and just use ellipsoids, which are 2 sigma confidence intervals of Gaussians. Here is the runtime profiling of GAPSLAM. On the left-hand side, I show that GAPSLAM achieves 100 Hz update frequency in the 2D range-only SLAM experiment. On the right-hand side, we show that GAPSLAM achieves 16 Hz update frequency in the 3D object-based SLAM experiment. We concluded that we achieved real-time inference for marginal posteriors encountered in SLAM. Future work can develop new inference techniques for the joint posterior, incorporate more complex multi-model measurement likelihood, and perform real-world active perception tasks. We acknowledge the generous support of these funding resources